Hey guys, hello everyone, welcome to Rasayan Academy once again. So here we are going to move onwards with another topic, that is pericyclic reaction. And this is a difficult topic and the question practice is very important. So let's start the discussion. This is the first question that I'm taking from the book itself. Alright, so yeah, identify the correct option and then I'm going to discuss the answer. Yes, what do you see? You see that there is a carbonyl in the system as well as a double bond. And ZnBr2 is nothing but a Lewis acid. So when the Lewis acid is going to connect to this oxygen like this, what happens? The oxygen gets a delta positive charge. And the alkene is now going to attack over to this carbon because oxygen becomes electropositive, and that's why the electron density pushes over to the oxygen side. But is the alkene directly going to attack over here with nothing else happening? Definitely not. This is going to be a concerted process. It is known as a ene reaction. Alright, it is a ene reaction which goes through like this, that the oxygen is going to attack over this proton, the bond falls up over here. You are going to get a cyclic ring like this, because this is how the carbonyl is going to become the OH now. There is the double bond and this is how you get the molecule. Now what about the stereochemistry? The alcohol is definitely going to form, but what is the stereo? Is it going to be below the plane or above the plane? This is definitely wrong. Both of these options are the same and they are also wrong, because definitely they are not going to be below. Let's see how it goes. So it is definitely going to go through a 6-membered transition state. Look at this. 1, 2, 3, 4, 5 and 6. It is going to go through a 6-membered transition state, which you can draw like this. Alright, here you can see that there is a carbonyl over here, and on third carbon, 1, 2 and 3, on the third carbon there is this methyl above the plane, and alright, there is this double bond which is present along with 2 methyls, one above, one below, like this. So I can put it up in this way. Also I can draw it in this way as well. Such that the methyl on the third carbon is present above and also equatorial. Alright, this way it is going to be more stable. So third position methyl, sixth position you are going to have the double bond. Alright, so what do you see when I'm looking at this molecule from over here? Let's say this looking on the molecule from the top. Definitely this alcoholic group is going to form above the plane. Below is a hydrogen over here, and this is going to attack. Alright, so this is how the product actually forms, and you can see that the OH and this methyl are on the same side, they are above, and this little alkene group is going to be now at the bottom. So C is going to be at the correct answer. OH is above and this group is below. Here the OH position is not correct, so C is the correct answer. It's a very simple ene reaction. Now let's move onwards to another question. What do we have over here? Just you have to answer what is going to be the major product over here, following the set of reagents. Okay. Yes, so what reaction, what product does it give? Alright, so first step, what do we see? We see that this is definitely going to form the sulfate or sulfonate ester like this, OS, PH, replacing the Cl minus from over here, pyridine taking up the proton. After this thing has formed, there is a possibility of a very simple reaction. That is, if you draw the molecule in this way, alright, what is possible? This kind of a 2,3 sigmatropic shift is possible. In this way. Now what happens next? In the next step we see there is a butyl lithium, that is there is a base. Now in the next step, if we see that this is the only acidic proton that you have, in the presence of a butyl lithium base in the first step, and in the second step RBr. So definitely you're going to replace this hydrogen group with another R group. 2R group have come over here. Now what is the purpose of this thing? Nothing, it's very simple. You are just going to replace this hydrogen with a R and get the same allylic alcohol. Alright, so the answer is going to be option number C, and these set of reagents are doing this by using the concept of 2,3 sigmatropic shift. This is a 2,3 sigmatropic shift. Other than that, if you don't know this or if you haven't practiced this, you will not be able to answer. Alright, so see, after this, the oxygen comes back over here and the sulfur has a pH again. Now this phosphine over here is going to attack over sulfur. This bond is going to open up and it's going to take a proton. Alright, so after that you finally get the same allylic alcohol with the hydrogen replaced by the R group. That is how it works, by using back-to-back 2,3 sigmatropic rearrangement. Alright, very simple. Next good question, which seems to be very obvious. What is going to be the major product? Yes, try this out. Very interesting, guys. There's a KH, which is going to behave as a base. Alright, I just make it O minus then. What else do I see? I see that there is a possibility of rearrangement. This is similar to a 3,3 sigmatropic rearrangement, a little bit extended, because 3,3 sigmatropic 1, 2, 3, 4, 5. It is actually that, but along with the Cope rearrangement, Oxy-Cope you can call it. It is a Oxy-Cope rearrangement which involves all carbon chain. Also a 3,3 sigmatropic shift that is also involving the ring opening of a 4-membered ring. It is strained, and that is why the reaction is very probable. Alright, so it's going to be an O minus as of now. Just writing the molecule as it is so that we know how the change is taking place. Alright, so this is where the bond connects. Now what will happen? Hydrolysis will happen to this carbonyl, and followed by that it will convert from the enol to the ketone. You are actually going to have option number C as the correct answer. Alright, so what was this reaction? Oxy-Cope rearrangement, and C is the correct answer. Very nice. Let's move onwards and do another good question. See, what is going to happen to this trans molecule in the presence of heat? Try this out. This could be a little bit tricky because you have to write it down in the favored conformation. Alright, so try that out. See guys, you have to write this molecule in the chair conformation, and it is going to be difficult because it is not a 6-membered ring. So yeah, you are only going to focus on these 4 at first, and then write the other ones. That is, whenever you write a chair conformation, definitely all the others are just substituentees. So you have to focus on these 4 points, most important ones. Alright, so what I did was I have drawn a Z alkene. This is a Z alkene over here in the chair conformation, and this is a E alkene. Alright, these 2 other ones, these are just extra substituents. Now after doing a 3,3 sigmatropic shift, how does it happen? The 3,3 sigmatropic shift is going to happen like this. That means over here a 4-membered ring is going to form, which I have drawn over here. Followed by that there will be 2 bonds, and those bonds are actually going to form like this, such that both of the alkene will become E alkene. Why? Because here the methyl was down, here the methyl was up, and after this 3,3 sigmatropic rearrangement, both of them will give you the E alkene. Here the hydrogen is above for this alkene, here the hydrogen over here it is below like this, and this hydrogen is up. So, both of these are E-alkene. I have, however, rotated from over here. This bond I have rotated. When I rotate, then this E-alkene, I can also write it in this way. Alright, so this is an easier way to write, in which we can understand, okay, both the alkenes are E-alkenes now. After, since there is a cyclization which has not happened yet, which will happen now. So after one more 3,3 sigmatropic shift, this is how it is going to become. As you see that now, if I just open this ring, it is both on the same side. Both of these methyls are going to be on the same side. Let's say both of these are downwards. That means both of these are below the plane, like this one. And both of the alkenes are also Z alkenes. Okay, so D is going to be the correct answer. A is wrong because there are 3 double bonds, which is not possible. B is wrong because it is trans. C is again wrong because of both the reasons. So D is going to be the correct answer. This is how it is going to be. Let's move onwards to next important question. Again, try this out. Very interesting one. Let's see if you can find out the answer. Yes, so these questions are for your practice. Even if you're not able to answer, it doesn't matter. You are learning something, so don't be disheartened if this seems to be very difficult. Just make note of these questions and see how we are approaching such questions. Okay, so here you see you have an acetal bond and an alcohol in the next molecule, and you have an acid. So in the presence of acid, always the acetal is going to break down. This oxygen is going to grab a proton and the other oxygen is going to push it away. Alright, after that it is going to become something like this. Looks like a ketone now, or a onium ion. Now this onium ion is going to be actually attacked by this allylic alcohol in this way. Alright, and after the attack, it is going to definitely push this over. After it is going to be removed, I'm just directly writing what we need. Alright, something like this. How am I going to get this double bond? Because when the alcohol OH attacks over here, this bond is going to open up. Then one more proton from here and the OMe, by taking a proton, they are going to eliminate and you are going to get a double bond like this. Alright, and we exactly need this double bond. Why? Because now we have got a vinylic and allylic ether system. I'm going to rewrite this whole molecule because whenever you spot allyl vinyl ether, you are going to see a possibility for Claisen rearrangement. Okay, this is how it is going to be. Yeah, definitely it is not connected to methyl. Those are different methyl groups. So let's just write it like this. Now after the rearrangement, this rearrangement is going to happen over here. Yes. I'm deliberately writing this on the top side, so it doesn't matter, alright? You just have to understand. This is how it is going to be. So how do I draw this? Yeah, where is the CHO? Here is the CHO. Whenever you see 1,5-dicarbonyl, 1,5-dialkene system, diene system, or allyl vinyl ether system, you are going to do a Claisen or a Cope rearrangement, that is 3,3 sigmatropic. Now if you again move it like this, 3,3 sigmatropic once again, now the molecule is going to be like this. How does it look like? It looks like this one, option number B, because there's a double bond and the methyl and the CHO are on the same side, and the other part of the chain has a alkene which is tri-substituted like this. So B is going to be the correct answer. What did we do? We have first generated the allyl vinyl ether system, and after that we did a 3,3 sigmatropic rearrangement, which is also known as a Claisen rearrangement. And after that we also did one more 3,3 that is going to be called as a Cope rearrangement. Why the difference? Because here it is a all carbon chain. We had to find out the 1,5-diene. If we recognize this thing, then definitely the reaction is easy. Here it is a allyl vinyl ether system. That's why the 3,3 sigmatropic shift is known as a Claisen rearrangement. Okay, so yeah, B is going to be the correct answer. Alright guys, let's try out this easy question over here. So here again you are getting an ester, and in the first reagent is LDA, second is tertiary butyl dimethylsilyl chloride. You can simply write as TBDMSCl, TBDMS, and the Cl leaving group. Then there is heat, and then there is HCl and THF. So try this out, very easy question. Alright, so while you are trying, let me also just draw this, and definitely guys, be honest to yourself and do this by yourself first and then see the answer. So this is going to be an E-alkene, and what about this one? This is going to just be an enolate. Alright, like this is going to be an enolate, but the problem is you are having a bulky group. So whenever you are forming the enolate like this and you are locking the enolate with the second step, you are actually locking the enolate in the second step with OTBDMS, and it's a bulky group. That means the enolate that you are going to form has got to be like this. The methyl should be away from the OTBDMS group. When is that possible? When you have E-enolate. Alright, the methyl should go inside. So this enolate is not going to work. It is not going to be a cis-enolate. It will be a trans-enolate. How do I know? I know because, till now, till here, it can still undergo tautomerism because O- is not locked. That's why the stereochemistry or the geometry of this alkene is not fixed. But when you are providing this bigger group, it is going to move this reaction towards this kind of an enolate. Okay. Yes. So E-enolate over here again. So now what is the third step? That is heating. You are going to do a sigmatropic rearrangement. How does it look like? Looks like this, but you definitely have to like convert this whole thing into a 6-membered chain maybe. Yeah, this is a E-enolate, so methyl is going to go down, and this again is E. There is OTBDMS, and the methyl is going to be like this. So once this is doing this kind of a rearrangement, OTBDMS. Now, since it is written like this, it might look like both of these methyls are actually on the same side. But we have to write all in the zigzag manner. Then we have to rotate this bond. Okay, so these methyls are not both below the plane. See, what I'm doing is I am rotating from here. So this methyl is still going to be below the plane, right on this carbon. It is still below. But this carbon I have rotated. Alright, so this carbon is over here. And then I'm going to write this thing. Double bond O, OTBDMS. After this, it's going to be hydrolyzed by the HCl, THF, and it's going to finally become the ester. Alright, so your final answer from ester to acid you are going to get. It is not going to still be like this, first of all, because you see that there is acidic workup. Secondly, it is not going to be cis. Alright, so all of the A, B, C, all the geometries are wrong. Only the D geometry is correct. It is going to rotate, right? You have to write this in the zigzag line, right? So that's why you have to rotate, and that's why both the methyls are going to show up trans. Let's move onwards to another very simple question. Try this out, guys. Very easy question. What do you get when these two molecules react? So for the reagents, in the first step you have butyl lithium, alright, and in the second step, since you are getting a 1,3-dithiene, you will have HgCl2 water or H2SO4, something like that. Yeah, dilute acid for the removal of this group. That's it. So yeah, try this out. So what is supposed to happen? Firstly, you see the lone pair on this sulfur might attack over this carbon, alright, and replace the bromine. If such thing happens, it is going to look something like this. There is going to be a positive charge on this sulfur. Now what is the butyl lithium going to do? Here, since there is a positive charge on the sulfur, these protons are going to be acidic. So it is going to remove a proton from here and give you an anion. This anion can very easily, it's very obvious if you see it, that it can undergo a 2,3 sigmatropic rearrangement, which is going to give rise to a more stable molecule, right? There is going to be one bond, one new carbon-carbon bond which forms, and one double bond like this, and the positive on the sulfur is also gone now. So this is a 2,3 sigmatropic rearrangement that takes place, followed by which you have AgCl2 and H2SO4. You know what does that mean? That means the removal of this whole group. So when you are hydrolyzing this molecule in the presence of, there's a hydrogen, right? So both of these are going to go away and you are having just a CHO. This is your answer. D is going to be the correct answer, nothing else. So what did we just use? We used the concept of Ampulang for doing this reaction. We also have involved a 2,3 sigmatropic rearrangement in between. So yeah, very simple. D is the correct answer. Let's move onwards to another question. Try this out. Alright, so here first butyl lithium is given. So that you can only see one proton which can be removed. And for this, definitely a lesser or a weaker base could also be used, like sodium hydride. But here butyl lithium is given. No problem. We are just going to remove the proton and make it O minus. That O minus is going to attack over magnesium, remove the bromine, because that is the only option it has, isn't it? और किस पे अटैक करेगा? ये कार्बन तो ऑलरेडी नेगेटिव है, right? So it cannot attack on the carbon. It is going to attack over magnesium and replace the bromine and get you this molecule. So how is it going to become now? Yes, there is actually a negative charge on this carbon, but now you see third step mein, this is going to be a pericyclic reaction like this. And what is our general stereochemistry? General stereochemistry means that both of these hydrogens are going to be on the top. That means these two groups are going to be on the bottom. So after forming a 6-member ring, I can write CH2O Mg still connected to this one, and methyl like this. After hydrolysis, this is going to get a proton, and this is also, because this is negative, is also going to get a proton. So finally your answer is going to be in this way. Alright, so this is your correct answer, option number B. The question was very simple. Move onwards. Next important and easy question. So what's going on over here? Let's see. Try this out, guys. You always tend to write the electron withdrawing groups endo. So we'll just do that. After doing this Diels-Alder reaction, it is going to look like this. The whole molecule is going to look like this. Alright, and what next? In the second step, you have a base. Now the base is definitely going to remove this proton first because this is the most acidic proton, followed by which you are going to get an electrophile PHCH2Br like this, on which it is going to do a simple SN2 substitution. So your final answer is going to be option number C. You have not yet removed this group, so it is still going to stay within the molecule. Alright, so C is going to be the correct answer. Moving onwards, next important question, ye dekho. This is an R group present over here with this molecule. What kind of a reaction is possible? Alright, try this out. Very simple. There's an R over here, and this is also an R. This is just typing mistake. Alright, yeah, try this out. Alright, so 120 degrees centigrade in the first step, second is metachloroperbenzoic acid, and third is a phosphine. So let's see what we can do with that. Now, first thing, whenever you see electron withdrawing group, this is definitely going to go endo. Along endo means it is going to go below the plane. And you know that these two hydrogens, if you have studied through my classes, you will know that the ones which are present over here, they are going exo, and these substituents, para, kind of para, they go below the plane after a reaction. So, or you can do one more thing. If you want to write it like this, that they are going above. Alright, this is also going above. For example, you want to write the enantiomer. Then you will also need to mention that this ester and this hydrogen, they are all above. Okay, so this is also correct, and let me tell you that by convention that what we usually follow, this compound, this is also correct. Both of these are correct, that if you write both of them below the plane, all of them below the plane, or you write all of them above the plane, both of these are the same thing. Okay, so yeah, now we are going to move onwards to the next step. We have done the pericyclic 4+2 cycloaddition. Next step is metachloroperbenzoic acid. What is that going to do? That is going to cause a heteroatom oxidation like this. Yes, the alkene is not going to epoxidize because heteroatom present hai, that's why it is going to attack over the oxygen first. Now what? Now again you see that there is a possibility of 2,3 sigmatropic rearrangement. After that, the molecule is going to look like this: oxygen and SPH. So definitely the SPH is going to hydrolyze now, and in the presence of, phosphorus has a huge affinity for sulfur, for removing sulfur like this. So it is going to attack over sulfur, sulfur attacks back, and the bond is on oxygen now. So basically the phosphine unit is to remove the sulfur, alright, and the rest of the molecule is going to be as it is. So B is going to be the correct answer. Alright, why the others are wrong? Because you are not going to remove these two carbons just like that. So these are just random options. Okay, and yeah, this is wrong because you cannot have the same stereochemistry of these two groups. And this oxygen also should be on the same side. If it is above, it is going to transfer from above. And from the very beginning, I told you all of these groups are going to be same. So if the oxygen has to come when we are taking the below groups, then this oxygen is also going to be on the bottom. So all of these are going to be on the same side. That's why A is also wrong. Okay,